Hello, everyone, and welcome back to our lecture 9 for our Blender course here. This week, we're going to be going over rigging. So, we go ahead and come down to the slides here. So, we're going to be looking at rigging and deformation in this lecture. So, this lecture marks a transition from object animation to character animation. And so far, our animation has focused on transforming entire objects, right? So we've been doing the entire object when it comes to animation. But now we're going to be looking at something a little different, right? So characters and complex models require internal control systems, and rigging enables controlled deformation of a mesh. So this lecture introduces the concepts behind rigging, and it is not going to go into some of the more advanced production techniques. This lecture is more about getting an overview and a basic understanding of rigging. And then from here, you will be able to rig models that you create and practice rigging. And then you will slowly be able to become better at rigging. So, where are we at in the course, right? We've learned mesh modeling and topology. We've learned about sculpting and surface refinement, and we have learned object level animation using keyframes. So we understand how Blender stores motion as data over time, and our scenes can move, but objects are still behaving as single rigid units. So the next step is learning how to animate parts of a model independently. Okay. And so the limitation of object animation, right? Object animation affects location, rotation, and scale, and these transforms apply to the entire object. But a character modeled as one mesh cannot bend an elbow using object transformations, right? And rotating the whole object does not create believable character motion. So internal motion requires a different approach, okay? And so, why are characters different, right? Most characters are modeled as single continuous meshes. And so, breaking a character into separate objects causes visible seams, unnatural joint behavior, and loss of smooth surface continuity. So, characters need to remain seamless while still bending and twisting, right? And this requires deformation rather than simple transforms. So, what changes with rigging? Well, rigging introduces a control structure inside the model, and movement is driven by an internal system rather than object transforms. Our geometry no longer remains rigid, and vertices are actually influenced by control elements, right? So animation becomes hierarchical, data heavy, and more complex to manage. Deformation as a core concept, right? Deformation means changing the shape of geometry, and vertices move relative to one another, and the object's overall transform may remain unchanged. So, what deformation allows is bending, twisting, and stretching, right? And character animation depends on controlled deformation, right? Especially if we have a humanoid type of character that needs to have elbows and knees, for example. We need to be able to allow at the elbows and the knees bending to occur, right? So, how is this lecture structured? We're going to begin by defining what a rig is, and then we will examine how meshes deform, and we will compare skeletal deformation and shape-based deformation. All right. And then we're going to explore how animation data scales when using rigs, and we'll briefly introduce tools for managing complex animation. So, we'll start by going from object animation to character control. So, moving beyond rigid objects. So far, our animation has treated objects as rigid bodies. So, a rigid object maintains its shape and moves as a single unit. And this can work well for props, cameras, and simple mechanical motion, but it doesn't work for our characters or flexible forms. Okay. So, what happens when we try to animate a character as one object? Well, rotating the entire character moves everything together, and scaling affects the entire mesh uniformly. So, no part of the body can move independently. And if we attempt to separate limbs into different objects, this introduces visual gaps, alignment problems, and artificial motion. So, the seamless mesh problem, right? Characters are often modeled as a single continuous surface, and the surface needs to be able to bend smoothly at joints, maintain volume, and avoid visible seams. And separating the geometry can break surface continuity, but keeping it unified prevents simple transform based animation. So, internal motion versus external motion, right? External motion, it changes the object transforms and it doesn't alter geometry. But internal motion changes vertex positions and it alters shape without moving the object itself. So, character animation depends on internal motion, and this requires deformation rather than transformation. Okay. So, why is deformation necessary? Well, joints need to bend without tearing the mesh, right? Surfaces need to be able to stretch and compress smoothly, right? And volume should be preserved when possible. So, armature settings such as volume preservation can reduce joint collapse. And deformation allows natural bending, organic motion, and expressive movement. And then we have the control problem. So, if vertices need to move independently, something needs to control them, right? Because if we wanted to manually animate thousands of vertices, it would be impractical. So, what we need a system that can group vertices logically, apply coordinated motion, and maintain hierarchy. And rigging solves this control problem. So, we're going to be moving from simple animation to structured systems, okay? And object animation is relatively simple, but character animation introduces hierarchy, influence relationships, and data scaling challenges. And motion becomes more of a system rather than isolated transforms. So understanding structure becomes essential. So the transition we're making, right? We're moving from animating objects to animating parts of objects. And we're moving from rigid motion to controlled deformation. And we're moving from simple keyframes to hierarchical animation systems. So let's go ahead and start by taking a look at what a rig is. So, a rig is a control system used to animate a model. It provides a structure that influences how geometry moves. And note that a rig does not replace the mesh, it works alongside the mesh, okay? And the rig determines how deformation occurs. We also have the armature object, right? In Blender, a rig is typically built using an armature. And an armature is an object that contains bones. Now, note that the armature itself does not render as visible geometry. It exists purely for control. And bones define the structure of the rig, okay? So, what a bone represents, a bone is a transformable control element, and each bone has a head, a tail, and an orientation. So, bones define regions of influence, and they are not pieces of the mesh, okay? Think of them as control handles for deformation. Again, bones are not geometry, right? They don't add vertices to the mesh, and they don't replace topology. They actually just influence existing geometry. And the mesh remains a separate object, okay? So deformation occurs through influence relationships. And bones are arranged in parent and child relationships. A child bone follows the transform of its parent, right? And movement propagates throughout the hierarchy. So, for example, the shoulder controls the upper arm, the upper arm controls the forearm, and the forearm controls the hand, okay? And this hierarchy mirrors anatomical structure, and it does so on purpose. So, why does hierarchy matter? Well, hierarchy creates predictable motion, okay? Transforming a parent affects all descendants, and this allows for coordinated movement. Without hierarchy, each part would move independently, and animation would become very difficult to manage, right? And do note that structure also reduces complexity, okay? So, how does a rig influence a mesh? The mesh needs to be bound to the armature, and then deformation occurs through an armature modifier that references the rig. And binding establishes influence relationships, and each bone influences specific vertices. So do know that influence strength can vary per vertex, and this helps create smooth bending instead of a rigid separation. Um, so rigging as a control system, right? The rig defines how motion is applied. The mesh responds to the rig's transforms, and animation keyframes are applied to bones. Geometry updates automatically, and the animator works with controls, not with raw vertices. So this helps separate control from geometry. So clean workflows separate modeling, control, and animation. The mesh stores form, the rig stores structure, and animation stores time based data. And keeping these layers distinct can help improve clarity when working. So, why does this system scale, right? Well, a character may contain dozens of bones, and each bone may have multiple keyframes. So, what hierarchy does is it keeps relationships consistent, and the animator manipulates structure rather than individual points or vertices. So, rigging makes complex character motion a lot more manageable. Now we can move on to looking at mesh deformation fundamentals here. So, first, let's talk about transform animation versus deformation. So, transform animation changes object location, object rotation, and object scale. But deformation changes vertex positions and the shape of the mesh. So, in rigging, the object transform may remain unchanged, and the visible motion comes from internal vertex movement. So, what does deformation actually mean then? Deformation is a geometric change, right? Vertices move relative to one another, and faces update based on new vertex positions. But the topology doesn't actually change, and only the spatial arrangement of vertices changes. Okay. How do vertices know where they're supposed to move? Well, vertices are assigned to vertex groups. Okay. And these vertex groups correspond to bones. So each vertex stores one or more bone influences and a weight value per influence. And the weight determines how strongly a bone affects that vertex. So vertex groups versus weights. Vertex groups are the membership lists, right? Which vertices are associated with a bone. And weights are the strength values, how much that bone affects each vertex. And to understand influence weights, so weight values will typically range from 0 to 1. A weight of 1 means full influence, a weight of 0 means no influences. And most vertices have blended weights. Okay. So blending actually allows us to have smooth transitions between our bones. Um, and why joints need blended influence? Well, if a vertex were controlled by only one bone, then bending would create sharp breaks, right? But a blended influence allows smooth curvature at elbows and knees and gradual surface transitions. So multiple bones can affect the same region, and this can help produce organic motion, which is what we're looking for a lot of the time when we're working with rigging and character animations. So let's look at the difference between rigid versus smooth weighting. Rigid deformation, each vertex follows a single bone, and it's useful for mechanical parts. But smooth deformation is where vertices blend between bones, and it's required for organic forms. So the type of weighting determines the behavior, right? And character animation will rely heavily on smooth deformation. And do note that game engines often limit the number of bone influences per vertex during export. So, some common deformation problems: collapsing joints, volume loss during bending, unintended twisting, stretching artifacts, and a lot of these issues often result from poor weight distribution. So, you may be wondering why automatic weighting is imperfect. Well, automatic weighting assigns influences based on proximity, right? It doesn't actually understand anatomy. So it could overweight some like certain regions, or it could miss subtle transitions. And clean topology and edge flow will help improve your automatic weight results. But manual refinement is often going to be necessary. And remember that deformation is data driven. So bones move based on keyframes, vertices move based on weights, and the mesh updates automatically. Remember that animation behavior is the result of stored data relationships, and understanding the data model helps diagnose problems. And then just finally on deformation here, why does deformation require iteration? Well, initial weighting rarely produces perfect results, and testing motion reveals some deformation flaws. So adjusting influence values improves bending, and again, rigging is an iterative refinement process. So clean deformation improves animation quality. So now we can go ahead and move on to look at a basic rig workflow. So let's first look at an overview of the rigging process, right? So rigging follows a structured sequence. The general process includes creating a control structure, positioning bones appropriately, binding the mesh to the armature, testing deformation, and then refining influence. And the process is very iterative rather than linear. So, first, creating the armature structure, right? The armature defines the control hierarchy, and bones are positioned to match joint locations and natural pivot points. So, good bone placement improves deformation quality. So, when you're placing your bones inside of your armature and matching it to your meshes, right? Be sure to try to have good bone placement initially, because it is going to help improve your deformation quality and reduce some of the work you'll need to do later, that will involve, fixing your bone placement. And structure should reflect intended movement. So, bone placement strategy: bones should align with anatomical or mechanical joints, and pivots determine rotation behavior. So, bone orientation, including roll, affects how rotations behave, and misaligned bones can cause twisting artifacts or unnatural bending. So, planning structure before weighting reduces later problems. Much like everything with Blender and working with 3D modeling, planning is incredibly important when it comes to working with rigging and bone placement. And then binding the mesh to the armature, right? So the mesh must be connected to the control system, and binding establishes influence relationships. So automatic methods assign initial weights, and the binding step does not finalize deformation. It creates a starting point for refinement. And then we have a couple of modes here, right? Edit mode versus pose mode. So in edit mode, we can define bone structure and adjust hierarchy and alignment. And in pose mode, we can animate bones and test deformation. And these modes serve different purposes, right? Obviously. And confusing them can lead to workflow errors. So do take note of whatever mode you are in. And then testing deformation early, right? After binding, motion should be tested immediately. Simple rotations can reveal weight distribution issues, joint collapse, and volume loss. And early testing prevents deeper animation problems. Always, always, always be testing. And then again, just iterative refinement. Rigging rarely works perfectly on the first attempt, and deformation issues require weight adjustment and minor structural correction. So, testing and refinement cycle repeatedly, and clean rigs support easier animation later. So, some clean rigging habits: keep your hierarchy organized, name bones clearly, avoid unnecessary complexity, test movement before animating extensively, and good structure simplifies debugging. So, why does workflow discipline matter? Poor rig setup can cause animation instability. Fixing structural errors later can be very difficult. And clean rigs can just help reduce data confusion and unexpected motion. So, remember that rigging is preparation for animation, it is not animation itself. Next, we can take a look at something called shape keys and morph based deformation. So, what are shape keys? Shape keys store alternate versions of a mesh, and each shape key represents a modified vertex configuration. So, the base mesh remains unchanged, and shape keys allow interpolation between stored shapes. and deformation occurs without bones. So, how do shape keys work conceptually? Well, the base mesh defines the neutral state, a shape key stores vertex offsets, and then a value slider blends between base shape and target shape. And the mesh updates continuously as values change. So, shape keys are value driven rather than hierarchical. Um, and then just looking at shape keys versus armature deformation, right? In armatures, we use hierarchical bone structures and control broad movement. And shape keys store specific geometric variations and they control localized shape changes. So armatures define motion structure and shape keys define surface change. So, when are shape keys most useful? Well, they're best used for facial expressions, muscle flexing, corrective adjustments, subtle surface deformation, and situations where hierarchy is unnecessary. So, more next, moving on to morph targets and fine control, right? Shape keys are often called morph targets because they allow controlled expression changes and gradual blending between states. And multiple shape keys can be active simultaneously, right? And blending can help create complex surface behavior. So, combining shape keys and armatures, most character rigs use both of these systems. Right, you use bones to control large movement such as arms, legs, torso, and shape keys refine facial animation and subtle corrections. And remember that systems can complement one another. Next, let's look at drivers and shape keys, right? So shape key values can actually be automated, and drivers can link bone rotation and other properties, and this can allow for corrective deformation. Our relationships become more data driven, and automation can increase control consistency. Again, shape keys require planning, much like everything else. They store explicit geometry changes, so too many keys can increase data complexity and organization becomes important. Remember, planning reduces confusion later, and clean naming improves animation workflow. So, when you're choosing between bones and shape keys, you should use bones when hierarchical motion is needed and large structural movement occurs. And you should use shape keys when localized surface change is required and specific expressions must be stored. And remember, the modeling problem determines the tool. So, strong workflows combine both intentionally. Now we can move on to managing rig animation within the dope sheet, right? So, why rig animation becomes complex? Remember, a simple object can have 3 location values, 3 rotation values, and 3 scale values. A character rig, however, can contain dozens of bones and multiple animated properties per bone. So the keyframe counts increase rapidly and animation data scales quickly. So we animate bones instead of objects, right? Keyframes are applied to bones, and each bone can store rotation, location, and scale. And the movement becomes distributed across the hierarchy. And coordinating motion requires organization. So the data explosion problem, more bones means more keyframes, right? More keyframes mean increased timeline density and harder debugging. And small timing changes can affect many parts. So managing data becomes as important as creating motion. Let's look at the dope sheet, just an overview of it, right? So the dope sheet displays animation data over time. It shows keyframes, object names, and bone channels, and it provides a structured view of animation information. And it can also help visualize timing relationships. So, how do we read animation data? Well, each row corresponds to an object, a bone, or a property channel, and keyframes appear as markers along the timeline. So, overlapping keys indicate coordinated motion, and clear visualization aids understanding. You can also edit timing in the dope sheet, right? So, remember, keyframes can be moved, scaled, and adjusted in groups. So, timing changes affect perceived motion. Remember, I believe we talked about it last week, but if the timing is too short, the motion can feel too fast, If it's too long, it can feel like the animation is happening in slow motion, right? And data level editing improves consistency, and organized keyframes simplify refinement. Um, Again, why does organization matter? Well, unnamed bones create confusion. Random keyframes can complicate debugging. Clean naming improves readability. Structured animation prevents accidental edits, and data clarity reduces frustration. Um, and rig animation as structured data. Remember, character animation is not just motion, it is a structured collection of hierarchical relationships, keyframe data, and influence mappings. And understanding the system improves control. So, clean data leads to stable animation. And then we can also move on here to nonlinear animation, right? So, from linear to nonlinear animation. Basic animation is created directly on the timeline, and keyframes are arranged sequentially, and motion progresses in a single continuous sequence. And this approach is called linear animation. Now, character work often requires reusable motion, right? So, what is an action? An action is a collection of keyframes, and it represents a defined animation segment. So, examples can include a walk cycle, an idle motion, or jumping, right? And actions can be reused across time, and actions also separate motion into manageable units. So, what is the purpose of the NLA editor? The nonlinear animation or NLA editor organizes actions, and actions become strips placed on the timeline. And these strips can be reordered, they can be repeated, or they can be blended. And basically, what happens here is motion ends up becoming modular rather than fixed. And why does modular animation matter? Well, complex characters require repeated motion, and rebuilding keyframes manually is inefficient. So, modular animation allows reuse, adjustment without rebuilding, and layered control. And remember that systems can reduce redundancy. We can also layer motion, right? So, multiple animation strips can overlap. And layers can help add variation, adjust intensity, and blend behaviors. And this supports a more expressive motion. So, nonlinear animation strips can manage both skeletal and shape key animation actions, and motion becomes compositional. And here we just have NLA and workflow discipline, right? So, modular animation requires planning, much like everything else, right? That's a core theme here when working in Blender. Cleanly separated actions can improve reuse, and poor organization reduces flexibility. So, naming and structure matter, and systems thinking improves animation stability. So, the big picture of animation systems: rigging introduces hierarchical control, the dope sheet manages keyframe data, NLA manages reusable motion segments, and animation evolves from simple transforms to structured systems. And remember, each layer builds on previous concepts. So now we are towards the end of our lecture here. I'm going to talk about the demo document for a second before just again summarizing some of the key points from the lecture and reading this week. Um, so the demo document, right? It's the supplemental document that I've provided on D2L for lecture 9, where you actually go through and get some hands-on experience with some of the concepts and fundamentals we learn about in the reading and the chapter and the lecture. So the purpose of the demo, right? The demo will reinforce concepts from this lecture, and it focuses on workflow awareness rather than speed. It also demonstrates how control systems influence geometry, and it shows cause and effect relationships. The goal is understanding, not polish. So, what will the demo demonstrate? Creating a simple armature, establishing a basic bone hierarchy, binding a mesh to the armature, observing deformation during motion, and identifying common deformation issues. So, observing deformation behavior, pay attention to how vertices respond to bone rotation, how joints bend under influence, and where distortion appears. And also notice how hierarchy affects motion, and watch how animation data increases with complexity. And then comparing systems during the demo, observe the difference between object transforms, bone transforms, and shape key adjustments, and notice when deformation changes shape versus moving the object. And also compare skeletal motion and morph-based changes. The demo is not going to go into advanced inverse kinematic systems, complex constraint setups, production level character rigs, optimization for game engines. Remember that the focus will remain foundational. So, how do you approach the supplement document? Work slowly and test frequently. After each major step, evaluate is deformation behaving as expected and does hierarchy feel logical? Save versions before making major changes and focus on understanding relationships rather than memorizing steps. So go ahead and go through that after you've wrapped up this lecture here. I'm just going to go over a brief summary of what we talked about, and then that'll be all for this lecture. So we talked about from rigid motion to controlled deformation, right? So we began with object level animation last week, and object transforms move entire meshes as rigid units. But characters require internal motion. So rigging enables deformation rather than simple transforms. And deformation allows bending, twisting, and expressive movement. We talked about rigs as control systems, right? So a rig is a structured control framework, and bones are hierarchical control elements. The mesh responds to bone transforms. Animation is applied to controls, not vertices. And separation of control and geometry can help improve workflow clarity. We also talked about influence and weighting, right? Vertices move according to influence weights. So smooth deformation depends on blended weights, and poor weighting can cause visible distortion. Deformation is also driven by stored data relationships, and rigging requires testing and refinement. We also went over skeletal versus morph-based deformation, right? Armatures control broad structural movement. Shape keys control localized surface variation, and both of these systems can operate together. So choosing the correct system depends on the modeling problem. And strong character rigs often combine both of these intentionally. And then we also talked about animation data management. So rigging increases animation complexity. More bones means more keyframes, right? But the dope sheet can help visualize animation data. And nonlinear animation can enable modular motion. So organization is essential for stability and clarity. And then the bigger picture, right? Modeling defines form, rigging defines control, and animation defines motion over time. And these layers remain conceptually separate, but clean structure in each layer supports the next. So, as a final perspective, rigging prepares a model for animation. Deformation replaces rigid object motion. Control systems reduce manual vertex manipulation. And animation evolves from simple transforms to structured systems. And understanding the system matters more than memorizing tools. So that is all I have for this lecture for this week. Please be sure to go through the supplemental document, get the hands-on experience that goes with learning the concepts and fundamentals we discussed this week, and actually applies some of the stuff we've talked about in the lecture and in the reading for the week. So go through that, and I will see you guys in the next video.